That's okay. We could actually just like work on it, like just
Okay.
behind us.
Okay, so what else is doing its thing?
Shoot.
Okay, so then what we end up doing. Hey, Jake said we don't have a pen. Because we want, what we essentially want is something.
Mm-hmm.
I want to draw a picture first. This is 50, and this is our unknown,
Mm-hmm.
and then it becomes this over here. 50. This is still our unknown. And what we're trying to find is so the change. What we're trying to find is the change of x. And what we have here is tangent equals opposite over adjacent, which then equals, well, one of them equals so that's essentially what it equals right there. This is where I get stuck.
Mm-hmm. So we're just trying to
So
find the
we-
change in x.
Yeah. Which means that we're looking for a change in the tangent, right?
I think so. Let's see. Did it say it wants like an equation or like a...
Who wants to know the change in the height between the two measurements? Any ideas?
I'm trying to think. There's an easy way to do it. I'm trying to think. Well, opposite over adjacent, of course. And
Should we solve for, well, should we solve for x for both of them first?
good.
Because we already know what the angle is for them both.
Mm-hmm.
Did I bring my calculator? I did bring my calculator. Oh, JK, I didn't bring my calculator.
I have nothing. This is sad.
Yeah.
Okay.
Okay, I suppose we can solve for the tangents first. So we have 38.5 degrees equals x over 50. X equals 50 times tangent of 38.5 degrees. See what calculator says.
Come on.
So this equals, what was that? 39.771795. That's for the first one.
Uh-huh.
Then for the second one, we have 8 degrees equals x over 50.
It's 40.2.
2 equals x.
So we're almost like half a foot off. 0.49.
What if we just cover up the whole board with math stuff? Let's see. Because we want to know x over dy. Is this one of those differences? Derivative difference rule? Because we would have f of x minus g of x. We find the derivative of that. Which in this case, then we would have wait, that doesn't quite make sense. Actually, because I think what we actually have here, instead of thinking of this as x's, if these are y's instead, and then our angle is our x.
Okay.
Because at that point, then that means that we know. So if we do one of these neat little integral thingamajiggies, we then have 38.5 and 38.8. What we have then is we're solving for f of x dx, or in this case, another way that we can write this, let's modify it. F of x1. Okay, we're going to pretend this is computer science because I don't know how to count any other way now. F of x0 dx. Does that make sense?
Yeah, it does.
And then what our equations themselves are is then tangent of whatever that thing's called, what, theta, equals x over 50.
That looks right.
And by x, what I actually mean is tangent of x equals y. Which then brings us back to the equation that we ended up over here, which then is 50 tangent tangent of x equals y, or f of x, then we can solve from there.
Mm-hmm. Is that what they just want? They just want it set up, or do they actually want us to? It's kind of vague.
I think they want the rate at which it changes.
Hmm.
So I feel like that's right, and like that's what we're supposed to be doing right there,
Mm-hmm.
except that that's not right.
Hmm. I mean, because we have, so like you said, x is, the degrees is like the x, and the
Yeah.
y is the height of that side of the right angle triangle. And we have, basically we have, you can do like rise over run kind of thing.
Mm-hmm.
What was it? Like x2 minus x1, y1 minus y1.
Yeah.
And so when you do that, at least when I crudely, it's for every 0.1 degree, it changes 0.143333.
Yeah, see, I feel like that's the answer that I would be getting, but I don't. Like,
It
I feel like we
doesn't feel-
did. Yeah, I feel like we did the process right, but that it doesn't fit because that's as the sun goes. Of course, the sun's coming up at this point, isn't it? I think I'm thinking about this way too much, or rather, it's way too hard.
It's okay.
What the heck?
It's lightning.
Twice of ones across elevation. Okay, so we're measuring the change of height according to what you would see. Which then I feel like that would be what it is. Maybe that is correct.
It's too bad you can't, like, there's not like an answer key, or at least she can give you the answer. So you know, like, okay, I'm on the right track, or...
Yeah.
I don't know.
That's kind of. I actually kind of like the my math lab
Mm-hmm.
because it has the show me how to do it, and then it gives you a different problem.
Yeah. It's, I don't know if it's the same company, but there's a website I used, like, in pre-calculus, and it helped me so much. Like, I aced that class because of it, and it's called interactmath.com.
Okay.
And it's exactly like my math lab, where, you know, it gives you a problem. If you say, show me how, it gives you a different problem, and then when you go back, it regenerates a new problem. But I really like that.
Mm-hmm.
The change in height between the two measurements.
Okay, so yeah, that is correct. And well, I'm pretty sure this is correct, except we have our formula. Well, I have the formula wrong here.
Okay.
Does that make sense?
Mm-hmm.
So we solve for that, those two places, subtract the smaller from the bigger, and then we end up with our answer.
Okay.
Which then is just this.
Those two answers, or subtract those two?
Subtract the smaller from the bigger.
It's 0.43.
Pretty sure that's how this works.
Mm-hmm. Okay. Yeah.
That looks correct to me.
Okay.
Okay, well,
Alright.
let's move on. Okay, an airplane files. Okay, I'm pretty sure that's what he flies. An airplane flies an altitude of 5 miles toward a point directly over an observer. The speed of the plane is 600 miles per hour. Find the rate at which the angle of elevation, theta, it's called theta, right? I want to go with theta, is changing when the angle is theta equals pi over 6 and theta equals pi over 3. Okay, so that means that this guy is asking us. So we have a plane. Okay, planes don't fly straight exactly.
Yeah, no, they really don't. Yeah.
But
Airplane
let's pretend that the world's only this big. So he's flying over a person standing right here. Oh. There's the plane right here. Wait, what is that? If it's pi over 6, that's what? Something?
Over 6.
30 degrees.
Oh, the angle, yeah.
So it's asking at 30 degrees,
is.
and then
At third.
at
What is that? That's 45.
I want to say it's 90.
So when it's 30 and then when it's right above them.
I believe so.
Okay.
Because we have 6, 5, 4. Let me check to make sure.
Oh, hey.
Because
We live in that age where we can do it now. Can't imagine like 20 years ago going to school. You're screaming.
Okay, let's see. In circle. Okay, so pi over 4 or pi over 6, yeah, it's 30 degrees and 90. Nope, 30 degrees and 60 degrees.
Okay.
Yeah, 643,
Find
that's
the
what it
range.
is.
Find the rate at which the angle of elevation, so that this angle part, right?
Yeah.
So find the rate at which the angle of elevation
So
is
we're
changing
looking at-
when the angle is 30 and 60. So between 30 and 60.
So we have 30, then we have 60.
I would say like that. So they're talking about the airplane, like the perspective of the airplane to the person in relation to the angle. Because like far away, it looks like the plane's probably not moving, but once it's like right above you, it's gonna go like.
Mm-hmm.
And so.
So that means that this is another one of those definite integrals where our options are pi over 6 and the top is pi over 3. Okay, and assuming that this world is actually flat that we live on, we have a vertical height of 5 miles. This is Minecraft, that's what it is. Where everything is just flat.
Minecraft. My cousins they're still into it.
Yeah.
They love it.
Okay. Wait a second. Okay, so how do we add in that 600 miles? Where does that go? Because that's not.
That's the rate in which it's moving.
Okay,
So that relates
means-
to angle. I want to say like, I mean, the height plays a difference, but that it remains the same. Like the height will never change.
Right.
So the two variables that are going to be that we need to figure out or find a relation is the speed of the plane, which we know is 600 miles, and the angle. So 600.
We have the angles. We have 30 degrees and 60 degrees.
So 600. So
What do we start? Or what are we trying to find here?
find the rate at which the angle of elevation is changing when the angle is 30 and 60.
Angle of elevation. The angle of elevation is changing, or
Find the rate at which the angle of elevation is changing. Yeah, so
okay. So then, what we're looking for,
it's like those two
Yeah.
angles.
like how fast are these changing versus how fast those are changing? Because these,
So yeah, okay, yeah, go ahead.
because these right here, we know that as being 5 miles.
Mm-hmm.
Mm. 5 miles. Great questions. Why is he looking at planes?
Terrorist.
I
don't know.
Why would he look at it?
I don't know. Just a weird guy. I don't know.
Getting nothing better to do.
Yeah.
You know, I'm just gonna read all these. Okay, so we have, and we draw more accurately too. So we have that at, so it's 30 degrees,
Mm-hmm.
which is the same as pi over 6. This is 5 miles. And then it becomes, that's even smaller. That should be 30, that should be the 60.
Yeah.
This which is 60 or pi over 3. This is still 5 miles. And we're looking for the change, the relationship between the two.
You know, I bet if you. I'm sorry. I wonder. Shoot. I'm thinking if we like flip the triangles upside down because the plane's not going to be in the same spot at each angle, if that makes sense. So we just flipped it upside down and made like the long leg its path. Because I'm thinking like we would find the distance that plane would cover in relation to the angle and height, and then you could find
So like,
the difference between the two. Yeah.
and this being the 30 degrees, okay.
Or, oh shoot, I didn't think of that. Because I was thinking like, because we got 5 miles here,
Wow.
and this was 30,
I
but
mean,
that would
that
make
still
sense.
works. This would
Yeah.
still work because those two angles are going to be the same. That makes sense.
Yeah, you can always switch between like sine and cosine. If we use like an x and y axis, but then like it's more and more.
Okay, so this is 30 degrees. This is 5 miles.
We could find. Well, we know all the angles. We know they're right triangle. I mean, we're using right triangles, so we can use any of the other angles if we wanted to.
I took the word ball.
That's okay. It's alright.
It's because 60. This is still 5 miles. And what we're trying to then figure out is this, right?
Mm-hmm. I don't know, is that like on the right track? If we know the distance of the plane is in relation to each angle, then we can calculate the rate and change with the angle.
I think so, yeah.
Because we know like it's somewhere, we kind of like we just did with the last problem. We have 2 points, like 2 x's or 2 y's, so to speak, but we need to know the other half in order to find a rate. I don't know. So,
Let's see.
okay.
Let's see. Okay, so that's what we're trying to solve for there.
Uh-huh.
The sad thing is we've done rate of change problems before.
Mm-hmm.
Just I don't remember.
I've never liked word problems, honestly.
All right. Any ideas?
I'm looking up rates, and I'm just like, why is this not clicking?
He was looking it up. I was like, this doesn't look familiar.
Want to skip it for right now?
Sure.
Go on the next one.
Okay. Security camera is centered 50 feet above a 100-foot hallway. It is easiest to design the camera with a constant angular rate of rotation, but this result is a variable rate at which the images of surveillance area are recorded. Therefore, it is desirable to design a system with a variable rate of rotation and a constant rate of movement of the scanning beam along the hallway. What?
So it wants it to keep moving, but not at the same. Go fast or go slow or fast slow. I don't know. So it's never stopping, I guess. Find a model for the variable rate of rotation if dx of dt equals 2 feet per second. What?
Find a model for the variable rate of rotation if the absolute value of dx over dt equals 2 feet per second. Okay, so variable rate of rotation. So that means that, I'm assuming that means that they can choose to have it sit in one spot and then rotate, and then sit in another spot and then rotate some more, versus a rate of movement of the scanning beam along the hallway. Wait, what?
These questions.
It is easiest to design the camera with a constant angular rate of rotation, but this results in a variable rate at which I forgot what I was just reading. Okay, but the results in a variable rate at which the images of the surveillance area are recorded. I have no idea what it's asking.
Okay, we'll skip that one too. Some of these problems are just so dumb. I'm like, why?
Okay, the range. This is a good one. It's shorter. The range are of a projectile fired with an initial velocity v0 at an angle theta to the horizontal is r equals blah, where g is the acceleration due to gravity. Find the angle theta such that the range is a maximum.
It's 45 degrees. Well, in the real world, it's 45 degrees. Because if you shoot, this is in my dynamics class, if you shoot anything like at a low angle, lower than 45, it'll go straight, but it'll be short. And if you shoot something high, it'll, does this. But 45, it's the highest.
Sweet. We don't have to use calculus if we're going to know the answer.
I don't know, like, it probably has some weird
it probably
response, but I'm like, real world application, no.
Okay. So we're going to assume that 45 is correct in the real world.
Yeah, I'm just like, I don't.
The range R of a projectile fired with initial velocity v0 at an angle of theta to the horizontal is r equals 2 theta.
You can answer those if you want.
Oh, they're just text messages. I'm stuck in this group message.
Whose group message?
My FHE group's group message.
Oh, that's cool.
Okay, so we have V0 equals initial velocity I'm assuming the range is the distance.
Angle horizontal is blank.
phase acceleration. So let's see, we have initial velocity times an angle divided by gravity.
Mm-hmm.
So then this is an optimization problem then
Mm-hmm.
we're looking at, which means that what we need to first find is r prime, or the derivative of r, which means that this is a terrible problem because now we're doing silly things with this.
Congratulations.
Equals v0 squared over g. Nope, that doesn't work. So let's see, we got g times the derivative of the top thing, which I'm just going to call derivative of top,
Uh-huh.
which is v2 sine 2 theta. What number is this for?
Yes.
So we have r equals v0 squared times the sine of 2 theta all over g. What we want to know first is not r kicking, but r prime equals g times v squared, and this is d is the derivative. Sine 2 theta minus 1 g0 squared of sine of 2 theta all over g squared.
Mm-hmm.
So that ends up being just that.
What ends up being what? Sorry.
Because this is a derivative of g times top, which is this long thing, which then becomes just 1.
1. Yeah.
Well, 1 times the top. Which means to get the derivative of that guy, we have to do the product rule, which then is 2v0 sine of 2 theta plus, that's a constant, right? Which means that this actually can go up to over here.
Constant?
Yeah, the 2 is. Is that how that works?
Is it above
Terminal
the side?
trick. It's
Like a power, or you know?
no, it's not a power. It's just like sine of 2 theta.
Oh yeah, yeah.
I don't. Is it? I don't know if it's constant or not. Sine or plus v0 squared. Sine is cosine. Is it positive or negative? Do you remember?
What is it?
The derivative of sine
Is cosine.
Okay, it's positive.
Positive.
I always have like the hardest trouble with that. Cosine of 2 theta. Which then I guess we can do like that sine 2 theta times 2 plus v that. Oh, no, just kidding, can't do that. Because that's cosine, not sine. My bad. But we can do it like this, where we have 2 sine 2 theta plus v cosine 2 theta, which is what that is right there.
Yeah.
So I'm not going to write the whole thing. I'm just going to put it right over there. Which then that needs to go too. Which actually it might be easier if I don't simplify this. And I just end up with which then will give us a 2GV sine of 2 theta plus GV squared cosine of 2 theta minus B. Well, I was really hoping that one of these would cancel out. But it won't because there's no G over here. Man. Yeah, I don't know.
I'm sorry, I'm not up right now. Like, all these times. Let's see. I think everything's okay. I mean, like, you can always just plug in that one variable and it would still work no matter what, either way.
Right.
I always have that
Just
trouble of
big and
knowing.
nasty.
Yeah. I always have the trouble of knowing, like, when to stop simplifying or sometimes oversimplifying actually makes it worse.
Yep.
Mm.
G squared. Okay, maybe. Find the angle theta such that the range is maximized. Can I see your calculator real quick?
Yeah.
Okay, so. So what if we just this in here? Oh, but we don't even know. How else is this gonna work? We have all kinds of variables in this thing. So, the problem that we have here is that the only thing that we know is g, because we don't know the initial velocity, and we're looking for the angle, so that we can find the distance. Well, so that we can find the rate of change, which will give us the distance. Yeah, I don't know.
Yeah.
I think it's going to be one of those where we don't know the answer to the question, and then we look it up once the
Probably.
the answer key is.
Most of these are just like, I don't know why. Sorry.
Well, it's already after 6:15.
It's a what?
It's already 6:15. Well, the velocities are constant because regardless of what angle that we shoot it at, the velocity is going to be the same.
Yeah.
Now, like over time, it'll change because of gravity. How long ago was optimization?
How long ago we did it?
Yeah.
It was early on, probably before 10, maybe.
Let's see.
I want to say it was at least the second week.
Day 3. 2D 2. Maybe I should mark this up better. Because all I'm seeing is just math problem after math problem.
Yeah, it's okay.